My university name is SungKyunKwan, and these are the name of the collaborators. Some of them are faculty members and graduate students in my university, and there are a couple of people who are outside our university. Since I am in China, I could not resist temptation to show you the Chinese character for my university, SungKyunKwan, SungKyunKwan. And if you can read Chinese, I think you know what this means, and it's very hard for me to translate in English. Apologize. Kwan means university. Established 600 years ago. Let me tell you a little bit about ADS research in Korea, and then I will move to ADS research in my university. We established a new department called Department of Energy Science about 4 or 5 years ago, supported by so-called world-class university program established by the Ministry of Education, Science and Technology. That department, since it is Department of Energy Science, we deal with all kinds of energy issues. Of course, photovoltaic cells and thermoelectric and fuel cell, and we deal with a lot of material research related to energy, like storage and hydrogen, and even energy conversion. And nuclear is just one of them. And in this department, we have about 9 foreign faculty members and 60 foreign graduate students. Now, to tell you about the current status of nuclear power plant in Korea, it covers about 32% of all the electricity produced in Korea, and there are about 20 nuclear power plants operating. And even after Fukushima, we are still constructing a few nuclear power plants, and we are still planning a few more. We need to go back to 1997. KARI, Korea Atomic Energy Research Institute, they had a 10-year ADS project. It was called HYPER, Hybrid Power Extraction Reactor. Started from 1997 and terminated in 2006. They designed this HYPER, what they call HYPER, with a K number 0.98, capacity 1 gigawatt, assuming that they use 1 GeV proton beam, and with mainly the purpose of transmutation of transuranic and fission product. And at that time, they did not think about thorium. And they designed the core in this way with some places for fission product and transuranic fuels. And they also constructed the lead bismuth corrosion experiment loop with electromagnetic pump and electromagnetic flow meter. However, at 2005, I believe, or 2004, Korea joined the Gen 4 consortium, and they stopped working on on the ADS project. And then they switched to SFR, and this I took this from internet last night. This SFR project has this timeline, and they are also working very well on pyroprocessing. So these two are main research works that KARI is doing. Now let me tell you about ADS research in my university. This is a schematic picture of the system. We can use an accelerator such as cyclotron or FFAG, as discussed by the previous speaker, which will impinge proton beam on the target to produce neutrons, and the thorium will be converted to uranium, and you know the rest of the story. And we, in the beginning, 5 or 6 years ago, one of the first aim we wanted to do was to do the computational simulation modeling calculation for this system, but we still haven't been able to do it. Now the kind of technologies that we work on can be summarized in this way. We have an accelerator expert in our group who actually developed and distributed more than 10 cyclotrons in Korea for medical purposes, and the most recent one was 30 MeV cyclotron with about 300 microamp. And the previous speaker gave an excellent presentation, and I'm very happy that I didn't prepare any presentation file for the accelerator technology. And of course, we need to develop reactor technology and fuel cycle, transmutation, partitioning, and also we need to worry about social economic issues, and with a lot of applications. So these are the topics that I will talk about. Computational modeling first. I will talk about what we call ThEC12, and partitioning, transmutation, design of a compact reactor core, and life cycle assessment of ADS. And if I have time, I will talk about detectors and medical applications. Now, ThEC12 is our name for nuclear data library. As you all know, ENDF is a well-established nuclear data format. However, it is written in ASCII, and in the world of computer science, having one language library like ENDF surviving in the form of ASCII is very unique, instead of evolving into some other form like C++. On the other hand, if we can make a C++ library out of ENDF that can be powered by software called Root. Root is a very versatile software developed at CERN in Switzerland. And then that library can be read and it can be used for processing and to visualize ENDF nuclear data, and very efficiently. For example, if you look at the ENDF file, it looks like this. It's hard to figure out what these numbers mean. And also when you want to do the Monte Carlo simulation, you need to go and fetch such data, but it takes time if you work with ASCII format. So we wanted to develop this C++ library of ENDF because ENDF is already a set of object, and object-oriented programming were the most natural choice, which is the C++. So we would like to develop user-friendly graphic user interface written in an integrated frame, which is Root. And we want to make this library fast enough to do the realistic Monte Carlo simulation. And we want to make it flexible and easy so that it can be used for education purposes also. Since it is based on C++, we constructed a lot of classes. This shows you the class structure. And this is one result. Compared to the bunch of numbers you just saw, if you want to plot certain data of certain file, then you just click certain menu, and then you can display like this, three-dimensional, and actually you can rotate. So this is a differential cross-section as a function of angle. And if you like to know what are these data, then you click this menu, and the library tells you what are these what these data actually mean, and you can plot the data in different ways supported by root. Now we have almost completed the first, so maybe the beta version, and we are in the process of converting this covariance data. And we hope to be able to release this soon. Now, let me talk about partitioning. As you know, minor actinide partitioning is a management way of high-level nuclear waste. And we have been developing green extractant to separate long-lived radionuclei, including actinide like americium, 241, 247, neptunium, and protactinium. And we also try to do the radiochemistry of thorium, developing a procedure for separating variables such as cesium-137, strontium-90, molybdenum-90 from irradiated thorium. And then there is a chemical called ThEC12, a well-known green extractant. It's organic, and we have been developing a way to separate minor actinide using this ThEC material. And by using the inert nature of thorium oxide and high solubility of strontium oxide in acid media, one can preferentially separate strontium over palladium, ytterbium, zirconium, and thorium from mixed thorium oxide. And then we need to decontaminate extracted fission products such as strontium from matrix thorium and fission product with a high decontamination factor. We use the so-called chromatographic resin to selectively extract strontium. This shows you how strontium is dissolved in nitric acid compared to other elements, and also in perchloric acid, 100%, as opposed to less than 1% of thorium. So you first separate, and then at the second step of separation, you do further decontamination by using chromatographic resin extraction method. And then by doing that, we can show that strontium is almost 100% selectively extracted, while thorium contamination level is less than 0.1%. And let me skip this. And also we have been working on transmutation of long-lived fission product. Let's take an example of technetium-99 and use a method called adiabatic resonance crossing. As you know, technetium-99 can be converted to technetium-100 by capturing neutron going through a gamma reaction, where technetium-100 will go through the beta decay and become ruthenium-100, which is stable. Now, for this to be possible, practically, we need to generate a lot of neutrons at the right energy so that neutrons can be observed, captured by technetium-99. How do you do that? Let's look at the neutron capture cross-section as a function of neutron energy. And this graph shows you the resonance peaks. There are a lot of resonance peaks. So if we can use these resonances then we can convert technetium-99 to technetium-100. So we need to produce a neutron in this energy range. And if we expand just this area, then I have this figure, which again shows you the resonance peaks. And in the beginning, the neutron has high energy, and the high energy neutron will be slowed down in the reactor and cooled to the thermal energy. However, we want those neutrons to have energies at this resonance peak. Let's concentrate only one resonance energy. And suppose neutron energy decreases from high energy, jumping like this, and then the neutron energy skips the resonance peak, which means N-gamma reaction will unlikely take place. So we want those neutrons to lose energy infinitesimally like this, so that resonance peak may not be skipped. So that's the aim of this work. And we use lead block because lead has a large elastic cross-section and it has a small capture cross-section, elastic cross-section and capture cross-section. So neutrons will survive and will just go through a lot of elastic scattering. Since lead is heavy, the recoil is small, so very small energy will be lost at each elastic scattering. So this is a design, lead block with a graphite reflector, with paraffin, and then polystyrene with boron to protect for the shielding. And after the simulation, we have this result. So there is a beryllium target that stops the proton and generate neutron. Neutron flux are formed this way. And if you put a technetium-99 sample here, then this is what you get. First, okay, this is again the same technetium-99 resonance peak that I showed you just now. If you look at the neutron spectrum at the beryllium target, then the neutron energy is peaked at high energies coming from proton, but we will shift this peak into this resonance region by using the lead block I showed you just now. And then now the neutron spectrum becomes like this. In particular, you can see the peaks in opposite direction. So there are disappearance of neutron, which correspond to the resonance peak, and this really shows you the working method of this adiabatic resonance method. So this is how we can transmute technetium-99, and we are designing now the target in a sort of engineering design way, and we are working further for the experiment. Now, our design for the reactor is still in a very primitive way, and we don't have much result to show you, so let me just skip. There is a method that we have been working on. It is called the life cycle assessment. It is for the social acceptance, because when scientists or engineers come up with a new idea, when it comes to a mega project like nuclear, we need to have it to be accepted by the society. And there is a method called life cycle assessment. It was developed by United Nations Environmental Program. Let's take a cell phone, and how much energy you need to make a cell phone or for use, or how much contamination or environmental impact is caused by using the cell phone should be properly evaluated, starting from material mining, manufacturing process, and when you use it, and when you dispose, and even including the process of recycling, and even taking into account the things like transportation and such. So that is called life cycle analysis, and there is a very good example of how useful this method is. We'll take an example of diapers. When the disposable diaper came to the market first, environmentalists objected because it can it's not environment friendly, as opposed to cloth diapers. However, if you take into account all the steps, considering material, manufacture process, use phase, and then disposal, land use, and recycle, then actually the life cycle impact comes about the same. So that's the kind of consideration we also try to make in the ADS. This diagram, this graph. Now, in the case of nuclear power, there are two main issues we need to think about. One is cost. The other one is carbon dioxide emission, greenhouse gas. And we show these two elements for different energy sources. Solar photovoltaic, solar thermal, and geothermal, natural gas, coal, and there are these three sources which we expanded here: nuclear, hydro, wind. So nuclear is really the best in terms of cost and also for the emission. However, when we calculate this, do we really consider everything about nuclear, like repository and nuclear waste? Actually not. And that needs to be properly taken into account. This is just to show that this graph can be grouped into two, like this and then like this. So we try to apply this life cycle assessment method to ADS. Now, conventional nuclear reactor case, there is a lot of energy that needs to be spent for treating the nuclear waste. However, in the case of ADS, nuclear waste is reduced, and so energy can be saved. Although there is some energy we need to put in for the reprocessing, so such a consideration needs to be done in a technical way. Let me skip. This shows you again similar schematic diagram of whole idea of ADS, accelerator, target, what they call energy amplifier and reprocessing. Now, to do this estimate, one needs to define the system boundary. In other words, suppose that there's a bottle here. Suppose you want to do the life cycle assessment for this bottle, and then there's a question of whether you really want to include the mining process or not. So that is called a system boundary, and we need to define the boundary, and that is called the cutoff parameter. And what are the cutoff parameter? So that is the first thing we did: construction phase, operation phase, deconstruction phase, and repository and landfill, for example. So for the construction, we need diesel fuel, for example, electricity, transportation, material. For the operation, we need mining, milling, conversion, enrichment, fabrication, and thorium supply. And for the deconstruction, and we need machinery, transportation, again, fuel and electricity, and such. So the question is where to put our boundary. And also to do the life cycle assessment, we need to know exactly how much energy we need to use for particular process, and how much material we need in a particular region, for example, in the US or in Korea or in China, because things have different value. So it's a lot of work. So actually, we soon realized it's very difficult to apply this life cycle analysis for the whole ADS project, for whole ADS process, because there are so many unknown. The technology has not developed well enough to give us numbers. So what we did as a first run was to apply this life cycle assessment just for pyroprocessing. So that was done with the help from Carrie, because Carrie has developed the pyroprocessing prototype recently, and they know how much electricity they need for cutting and decladding, for example. They know how much electricity and material they need for electro refining. They can even tell us how many cranes they need for the process. So we collected that information for this pyroprocessing, and we came out with this number for greenhouse gas emission. So you can see that most greenhouse gas is emitted in the process of electro refining and electro reduction, electro winning, and slate waste treatment. Now detectors, and we do a lot of medical application. We have been developing a gas detector called Micromega with the CERN, with the people at CERN. And I'm sorry, this is wrong. And we also develop online detector for alpha particle detection. Because for example, when we have an accident, there will be alpha emitted, and we can detect alpha online by using optical fiber. So we test it with the thorium source, and alphas are emitted on CR39 film, and then reflection of the surface reflectivity of the surface changes when the alphas hit the surface of the film. So by using the laser beam in the optical fiber, we can detect whether there are alpha particles coming or not. So such a research was done and published, and we also do the simulation for slightly different purposes. And we are developing this Micromega's gaseous detector for neutron and also other particles. Thank you.
Your life cycle assessment of pyroprocessing, have you got any life cycle assessments of other nuclear reprocessing techniques to compare that with?
I'm sorry, I didn't catch that.
Yes, you've undertaken LCA for pyroprocessing, but have you got any LCA of other reprocessing techniques, such as Purex, to compare that with?
No, not yet. Yeah, we just finished this recently. If you can actually give me an idea, then we can try to work on it. Yeah. I think this is very useful tool to the public. so that nuclear is really useful.
Your ThEC program looks really nice. How do I get a copy?
At the moment, we almost finished, but we are trying to make it look nicer and more easier to use. And there are small bugs, like sometimes when we click certain menu, nothing comes out or wrong information. And there are some small bugs. We are in the process of correcting those. And then we can release.
Takaki from Tokyo City University. My question is concerning on transmutation of technetium-99. Did you compare the transmutation efficiency, your new method with pure summarized transmutation?
I'm sorry, I don't have the figure table. Actually, we did the test for 50 MeV proton because we have a beam of 50 MeV in Korea. And of course, the yield is very small because of 50 MeV limitation. And I didn't compare that with the thermal neutron. I'm sorry, I cannot directly give you the answer.